Welcome to today's webcast entitled Making Accurate Signal Integrity Measurements Using a Vector Network Analyzer, brought to you by Keysight Technologies. I'm Kim Brown, and before we begin, here are a few brief announcements. This webcast is part of the Keysight Engineering Education Series. To register for other webcasts, visit keysight.com, find webcast series. Let me introduce today's speaker. Mike Russo is a Signal Integrity Application Scientist in the Internet Infrastructure Solutions Group of Keysight Technology. He has over 30 years of experience in the test and measurement industry. His background includes the design and development of electro-optic test instrumentation for aerospace and commercial applications. His most recent activity has focused on the complete multi-port characterization of high-speed digital interconnects using time-domain reflectrometry and vector network analysis. He has authored over 30 professional publications, including 2 books on signal integrity. Mike has been awarded 1 U.S. patent and twice received the Agilent Spark of Insight Award for his contribution to the company. He received a Bachelor of Science degree in Electrical and Computer Engineering from the University of California. Now on to today's presentation on signal integrity.
Good morning and good afternoon, everyone around the world. Thank you for joining us today. Today we're going to talk about some very interesting engineering topics surrounding the use of vector network analyzers. Although it says vector network, that's not exactly correct. We are talking about vector network analyzers for signal integrity measurements and applications. So a little bit of the agenda, what we're going to be talking about today. Of course, making the measurement is the most critical part of using a vector network analyzer. But the first thing is talking about how to prepare the instrument for that. We'll go through some calibration techniques. Fixture removal is a critical part of that, so we'll talk about that. Then, of course, acquiring the channel data. And so we'll have to look at multi-port S-parameter measurements and how those are acquired. And then finally, we'll talk about analysis and looking at the channel performance, both single-ended versus differentially, and then some of the common performance parameters surrounding the digital domain, such as eye diagrams, channel operating margin. And then we'll talk about future trends. And if we have time at the end, I'd like to sneak in a little demo, and we'll see how the time goes. So, preparing the instrument for the measurement. A lot of people wonder, why do we even need to calibrate? I've got an instrument in my lab. I don't calibrate it but once a year when I send it back to the factory. Well, vector network analyzers are precise instruments. And so, we recognize that it's impossible to make perfect hardware because of the architecture and topology of any instrument. And even with the highest quality components, some errors are introduced just because of device physics. So what we're going to talk about today is how to get the accuracy that we expect for our really demanding applications in the internet infrastructure. Well, we do something called vector error corrected calibration that we'll talk about. And that's different from the annual calibration that's done at the factory. This is something that you do as the engineer in the lab right before the measurement. And what does the calibration do for us? Well, removing the largest contributor to the measurement uncertainty is what we want to achieve. And we'll talk about various types of error, systematic error being the largest. And the ultimate goal for us, of course, is getting the best true performance of just the device under test. We don't want to measure cables. We don't want to measure fixtures. We want to measure that device that you're designing to go as fast as you can somewhere in the channel transmitting high-speed digital data. Now, just as an overview, I wanted to show this slide to appreciate the complexity of any instrumentation. Calibration is an important factor where all of these different aspects need to be considered. And quite easily, you could take the calibration of a VNA and turn it into a semester-long graduate program. But you know what? I think that we can give you a very intuitive feeling in the next 40 minutes of what it does and how we can use this as a tool in the lab to be successful in our designs. But there's a lot that goes into it, and we're going to talk about the basic fundamentals so you can appreciate what you're doing actually as you go through the process. So you'll hear people talk about things called measurement error modeling. And there's basically three categories of error when you talk about a vector network analyzer. The systematic errors, these are the ones that are due to imperfections in the hardware of the analyzer and the test setup. So these are time invariant. So we can predict these. And fortunately, these are generally the largest sources of error that we can remove with calibration. So this is the main goal of doing a calibration. And the other types of errors, random errors, these vary with time, and they're very random, so we can't predict what they're going to be. They're caused by things like instrument noise, device physics of the actual components inside the instrument, the repeatability as these high-frequency switches turn on and off, whether they're solid state or mechanical switches. And the random errors, there's really nothing you can do. And this is true for most instrumentation. The last category of errors, what we call drift errors. These are system changes that happen after calibration, caused mainly by temperature variation and even cabling. So I'm going to show you some tips and tricks about using cabling in a way that will minimize drift errors, but you can always recalibrate and take those drift errors away. But there are certain things that we can do to avoid those in the first place, and so we'll get into that soon. If you look at the topology inside the architecture of a vector network analyzers, there's various components inside. Looking at from the left to the right of this flowgram, there's a very precise sine wave that then gets split in two different directions, a very high frequency splitter. And then it goes through a directional coupler, through some cabling, eventually going to device under test. And of course, a vector network analyzer gives you reflection and transmission parameters. So there's various errors that we can correct for that are systematic errors. So the errors relating to signal leakage are directivity and crosstalk. So these errors related to signal reflections are actually source and load match. So the errors related to the signal reflections sometimes are called match or mismatch, depending on your point of view. So the final class of errors related to frequency response of the receivers, and these are what we call reflection and transmission tracking. So we can get the full two-port error model, including all 6 of these terms for both forward direction and reverse direction. And this gives us the total of 12 error terms. So this is often why we refer to a two-port calibration as a 12-term error correction. Now, I like to show this slide just because it gives us a model of how to think of the multitude of error correction techniques that can be employed. And many of these terms are misused, and the nomenclature can be confusing. It seems like an alphabet soup. But let's start by just thinking of 2 main categories of error correction: pre-measurement error correction and then post-measurement error correction. The blue circles are pre-measurement, and these are things that we refer to normally as calibration. So you'll see short open load through, which is SOLT. You hear that used a lot. TRL, through reflect load, and then variations on TRL like LRM, LRL, things like that. Those are all done before the actual measurement. The other category is post-measurement error correction. And you can see here, S-parameter de-embedding, port extension, and time domain gating are the most popular post-measurement error corrections. And the main concept here, if you plot simplicity versus accuracy, most of these are pretty linear, which what that means is that the more energy and time and sophistication you put into the error correction technique, most likely you're going to get a more accurate answer. And that's not to say that the simple ones are not good. You can use time domain gating in the lab in a very quick and easy way and get valuable information. But if you're making very big decisions financially or publishing data, S-parameter de-embedding is probably the best way to go. So this is an overview. It's not meant to be very quantitative, but it's just a general feeling of kind of looking at all the different error techniques at once. Now, there have been some emerging techniques that have kind of put this paradigm upside down. So there's an outlier to the linear curve, if you draw it here, called automatic fixture removal. And there's a new family of error correction techniques where you can actually get very good accuracy similar to TRL, but it's quite easy to implement. And the reasons for that I'll go into very shortly here. Now, SOLT, what did we say, what type of error correction this is? Pre-measurement or post-measurement? Well, this was the blue circle, so it was pre-measurement error correction, which we can call calibration. And there's a couple different ways to do that with either a mechanical cal kit, which is in the lower left-hand corner, or you can use electronic calibration modules, which are on the right-hand side of the slide. Now, there's advantages, disadvantages of each, but basically, for high-speed digital applications, especially backplanes, there's so many channels that need to be measured. We find many labs doing multi-port S-parameter measurements, not just 4 ports, but 12, 24, 32 channels. In that case, you almost always want to use electronic calibration modules. They're easy, they're fast, they save time, and it prevents connector wear. If you're in, I would say, a metrology environment where you have a lot of time in R&D and you've only got a mechanical cal kit, use it. That's not a problem. But practicality, in my experience, has shown that ECALs work very good, and I use them personally all the time myself. Now, another type of error correction we talked about was TRL. And TRL is a way of moving the reference plane closer to the device under test. And it can be used to remove fixture effects. It's good for non-coaxial environments, and it characterizes those same 12 systematic errors we talked about. The challenge here is the user must fabricate this calibration standard. And in the lower right, you can see that there's 5 different standards that need to be designed and fabricated for TRL calibration. A through, line 1, line 2, line 3 for 3 different frequency bands, and then a reflect, which can be either an open or a short. So this has been used in the microwave application area for decades, and it's proven to be very reliable, but it's not been that easy to implement. And the reason is you end up having to build these type of calibration kits. And here's half dozen or so that we've used before in the laboratory, and you can see that you have to have a very good impedance control that matches the fixture that you want to remove or the reference plane that needs to be adjusted. And so it can be done, but you just need to spend a little more time building these kits. So this is an alternative. Also, all of these error correction terms that we discussed, many of them can be combined to do what's called a 2-tier calibration. For example, you can do short open load through with an ecal all the way up to the end of your test cable. Then you could do a TRL right before the device under test to remove a test fixture. So you can do some interesting combinations here, and this is kind of the flexible and interesting part of making measurements. Now, So what kind of things can we do in the lab to make our measurements more accurate? And these, some may be obvious, but tell me how many of you have taped down cables when you're making measurements. Why would we want to do that, as we've done in this picture here, testing a USB 3.0 device? Well, it turns out, remember those drift errors we talked about, where you can calibrate the instrument, but over time, temperature, and any cable movement, you'll have drift error introduced, and it may force you to recalibrate. Well, if you take care in not flexing test cables too much, you can avoid introducing what are called phase errors, or difference in propagation velocity due to bending the dielectric in these test cables. So this is something that's a little bit of a trick that I see many people use, and it actually works. What else can we do? Well, first of all, make sure your eCal and your mechanical cal kits are up to date. They've been factory calibrated. Make sure they're all very clean coaxial connectors. You can get in there with a little Q-tip and some isopropyl alcohol, and we've got a whole application note on connector care. So as you can imagine, these test cables are quite important. And make sure you invest the money into the test cables after you've invested all the money in your vector network analyzer, right? You wouldn't put bias ply tires on a Ferrari, right? This is the same idea. So spend the money, get some nice cables. If you suspect the cable is bad, replace it. Okay? All right. So now let's talk about the channel data acquisition. So a day in the life of an SI engineer. Now that we've got the instrument ready, what kind of things do we need to think about? Well, we have to think about what testing parameters, what frequency range we need, how many ports. One differential channel is 4 ports, right? So if you have 3 differential channels that you want to test at the same time, how many ports is that? Well, 3 differential channels, 6 input, 6 output, that's 12 ports. Is your device active or is it passive? Are you going to probe your device or are you going to use a test fixture? What specialist software tools or accessories do you need? So if you choose some of the right tools, you can save a lot of time in the lab. So do your research, ask your colleagues who are making similar measurements what tools they prefer, and a lot of times you can get free software downloads on a trial, and you can try something for a month or whatever. So keep these things in mind. Now, what kind of frequency range is possible and how many ports can you get? Well, we have a whole family of network analyzers, and if you're in the R&D lab making very high frequency, ultra accuracy required data, you can use something like this system on the left. 4-port, 120 gigahertz performance network analyzer plus physical layer test system software. And as you can see, there's 4 remote heads here that are designed by Keysight that are configured and integrated into a system to have a broadband sweep from a very low frequency all the way up to 120 gigahertz. This is extremely valuable if you're doing very high data rates. And with 56 gigabit per second, 112 gigabit per second, there are labs around the world that are now starting to look at this type of equipment. On the other end of the spectrum, we can go all the way up to 32 ports on a system like this on the right. This is a PXI-based performance network analyzer, and we use this industry standard chassis with plug-in modules, and each plug-in module that slides in vertically here is a 2-port vector network analyzer that can be scaled as your requirements are accelerated. So you can start this with just 4 ports and then expand it all the way up to 32. And of course, there's a whole family of network analyzers in between. We've got portable network analyzers. We've got benchtop. We've got these production-oriented network analyzers that are very scalable. So basically here, I just recommend take a look at our website, and you can get a very good indication of what's available there. Now, when we think about active or passive device testing, it may not be so obvious. It may be obvious, but sometimes you can have any of these types of components that can be measured by a vector network analyzer. And they have various levels of linearity and passivity. And the point that I want to make today is we're focusing just on the passive devices that you see here: backplanes, printed circuit boards, cables, connectors, and even the IC packages. So we refer to these as linear passive devices under test. Another decision that a company has to make is, are we going to invest into a probing system and develop intellectual property around probing measurements and develop a library of probes and data that are related to that? Or do I try and do fixturing? And there's advantages, disadvantages to each. Of course, probing is very flexible. All you need is to have the right probe pitch and the right configuration, ground signal, ground, or whatever the device requires. It can be expensive. It doesn't have to be all the time. Sometimes you can get something like at the bottom of your slide here, where it's just an arm, an articulating arm with a probe and a heavy base. So you can get started without getting a full-on probe system. But normally, if you go into a full-on probe system, they do get a bit costly, and you do need these integrated substrates for calibration. Set the reference plane at your probe tip. So remember, we talked about short, open, load through. Well, you do the same thing with the probe system and a probe, and you'll probe short, lift up the probes, probe and open, and probe a load, and then a through, and you'd have two probes and do a through path. On the other hand, fixtures, they're very easy to use. Basically, you just plug them in, or you would torque them if it's a coaxial connector. The disadvantage is each connector type or application requires a different fixture. So in this case, you may have a dozen different fixtures, and most likely you would want to have a library that has all of the S parameters for each one of those different fixtures. And that would allow you to de-embed the fixture at the reference plate right at the input to your device under test. And that is a very effective way to get your device performance. Okay, so now let's talk about analyzing the channel performance. Traditional channel performance parameters are things that you may be familiar with: insertion loss, return loss, characteristic impedance, near-end crosstalk, far-end crosstalk, eye diagrams. These are very traditional ways of measuring linear passive interconnect using a vector network analyzer. And this is very straightforward, but there are emerging standards that are being proposed today that add complexity to things. And as a test equipment vendor, we need to stay half step ahead of what you're needing today. And so we are constantly going to standards meetings, trying to look at understanding these new figures of merit. Some of these, one of the more familiar PAM4 eye diagrams, stands for pulse amplitude modulation. And then you may be hearing new terms like channel operating margin or effective return loss. These are a little more complicated, so I think it's worth mentioning a little bit about these. Oh, by the way, just to go back, this graphic here, this picture is a Zowie backplane extended attachment unit interface running data at 3 and 1/8 gigabit per second. And you can see the vertical PCB test cards that are actually test fixtures with the gold coaxial 3.5 millimeter connectors. And this is where you would torque the test cables to. And so this is a very typical channel that would be analyzed for a backplane in a router or a switch in a network data center. But all of these things we're talking about today also apply to cables, connectors, C packages. Okay, channel operating margin, what is it? Basically, it means different things to different engineers. If you're a SerDes engineer, serializer, deserializer, transmitter, receiver type designer, Comm is a reference chip capability. So this will help you decide the signal-to-noise ratio budget of your receiver, which is a very critical thing. Now, if you happen to be a channel designer, what Comm can do for you is help you decide what the air budget is between all these different performance parameters, like insertion loss, return loss, reflections, and crosstalk. You know, what questions that you could ask, which one of these are going to make my system fail? And in my particular device, is it more susceptible to one of these failures than others? And also, Comm can be a tool that will give you some trade-offs that you can make between your air budget. How good does the VIA design need to be? What materials do I need to use? PCB constructions, do I need edge-coupled differential pairs or broadside-coupled are okay? What connectors do I need to use? So channel operating margin can help you make more of these system decisions. This, what we're looking at here, is what's called a Comm configuration spreadsheet. And this is something that has many different variables in it pertaining to parts of the channel, both active and passive. And so typically, the way that we would measure with the vector network analyzer is we would first measure the passive channel, just like that backplane that I showed you. So we get the S parameters of that backplane. Then within our software tool, physical layer system, what you would use is a Comm algorithm called within a MATLAB script, or you can have a Python script, it's your choice. And you would basically call this configuration spreadsheet and would run through the subroutine, and using the S parameter data that you measured, that's very accurate because you calibrated your instrument properly, Comm would end up giving you a result that looked something like this. And the Comm figure of merit itself is one number. So if you see on this second plot from the top left, there's a green box, case 1, case 2, 8.5 dB, 8.1 dB. This is the Comm number. So channel operating margin in this case 1 is 8.5847 dB. And so what we're doing is taking all of these active and passive parts of a channel with all the different preemphasis, equalization, and various numbers of taps that are defined inside that configuration spreadsheet and apply them to this S parameter measurement that we made on the backplane. And this gives you CTLE response plots, PDF plots, pulse response. There's some bathtub voltage curves here, insertion loss deviation, insertion crosstalk ratio. So all of these can be automatically displayed by executing that MATLAB script, calling that configuration spreadsheet. And if you need to troubleshoot beyond just the one number of Comm, for me, I like to know, where does that number come from? If it's failing, where do I start looking for failure root cause? Well, this is when you start diving into each of these plots and analyzing what went wrong. Okay, besides Comm, one of the trends that we're seeing in the industry is multi-port S parameter measurements. I mentioned that 3 differential channels requires a 12-port VNA measurement. And when you start getting 144 elements in your S-parameter matrix, you start, frankly, having data management challenges. And the best way to address these issues is naming your ports. As you look at your device under test, you obviously can physically allocate a number or a name to each port. Put this information into your tool. Let the tool topology be clear and let it be saved with your S-parameter data. You know, how many times have you been asked, oh, gee, I'm not sure I believe that data. Can you make the measurement? Or, gee, did I have a bad cable? Is that one channel that's an outlier really true? Do I need to go back and retest? How do you know where you hooked up each of these 12 channels? So this is a good way to keep track of the multi-port S-parameter data, and the tools will do the work for you. So calibration, measurement, and analysis can all be done with these types of tools. Okay, PAM4, why do we need it? Of course, we've got a lot of increased network bandwidth demand, and the data centers are growing. 400G links are being designed. All of these trends are forcing us to be more creative with the ways that we modulate our data. And so you'll hear about PAM-N. And so today is PAM4, maybe tomorrow's PAM8, and in 5-10 years it'll be PAM12. So this is something that we're going to be seeing more and more of as the data demands become greater. And most of you have probably seen a PAM4 eye diagram, but for those that may have not, in the upper right vignette, there's a typical NRZ, non-return to zero eye diagram. And then the bigger plot here is the PAM4 eye diagram. And so we have 4 logic levels in 1 bit period, 0, 1, 2, and 3, which gives us 3 eye diagrams. So previously, where we had maybe 1 rise time, you now have 3 rise times. And previously, with NRZ, 1 fall time, we have 3 fall times. So this is the next generation of multi-level signaling that we'll be using for many years to come. How do I measure it? Traditionally, what's been done is you get a pseudo-random binary sequence pattern generator. You drive your device under test, your linear passive device. You measure the output of your device with an oscilloscope, like this 86100 DCA, and you get your PAM4i, and you can do all the eye analysis that you typically would want to do. Newer methods that are starting to be integrated into standards are measuring the S parameters of your same passive channel with the vector network analyzer. And then you can synthesize the PAM4i mathematically. And this has proven to be very accurate. In fact, the routine that we correlate back to the 86100 DCA is the same algorithm. And you don't need to remember this, but basically you would take the S parameter measurement and derive the impulse response of that. Then you would drive with the virtual PRBS pattern and do that convolution of that impulse response and the PRBS. And then you'd get a very long data train, and then you just fold that over every bit period on itself, and you would get this PAM4i diagram. And this correlates very nicely. So there's more than one way to do these sorts of measurements. Okay, so let's talk about what's next and some future trends. So now that we have accurate S parameters, we understand the calibration process. We know what types of parameters we need to look at, and even if we have some more complex measurements, we can do those. What do we do? What's the plan? Well, we want to prepare the data for analysis, and dissecting the channel data is really helpful in the troubleshooting process. You can explore the design space with something called pathological channel analysis. Basically, that's just a fancy word that describes a method whereby you would do a design of experiments and you would introduce various levels of pathologies, but you only inject one pathology at a time. For example, crosstalk. You would inject different levels of crosstalk only into your channel, and you would see how susceptible your channel is to being a failure due to only crosstalk. And that would be the design space of crosstalk. Then you can go and add insertion loss, 3 dB, 6 dB, 12 dB, and see how your channel performs with increasing levels of insertion loss. So if you're interested in this pathological design space, there's the DesignCon paper that we did in conjunction with Rod River Technology back in a year or two ago from DesignCon. Other things that we want to do, we can extract material information. What type of dielectric do we need to use to get the performance we want? We can analyze the TDR impedance profile. For me, being a digital designer, this impedance profile is one of the most intuitive tools that you can use. You actually can assign every excess inductance or excess capacitance inside that impedance profile to a physical structure inside your channel. And what this allows you to do is to physically isolate crosstalk generating structures inside your channel. And so we've got application notes that talk about that in detail on our website. And I'm going to give you some of those resources very soon. Single pulse response. Single pulse response is another new emerging way of measuring our channels. Keysight Educational Forum at DesignCon 2018, we had a paper that was very interesting that you can get off the web about single pulse response. I think this is going to be very interesting because it basically is the blink of an eye. So whatever eye diagram analysis you're used to doing, you can see what one bit going through a channel will do. So this is interesting. Finally, one of the most important things that I think we should be doing more of is correlating measurements with models. The power between this simulation, guessing what the performance will be, building a prototype, and then comparing the measurement of the prototype to the simulation is extremely powerful and gives us a lot of capabilities of hacking the backplane or things of this nature. So these are all future things that we'll be doing once we get these little golden nuggets of accurate S parameters. So in conclusion of the slide presentation here, we know that VNA measurements requires an understanding, or at least an intuitive understanding of what calibration error correction do for us. And we have various hardware, software configurations that you can use in your lab that will make your day-to-day job easier and, frankly, more interesting. And we know that error correction is a necessary thing that we must do to obtain that true device under test performance. Viewing the measured data in different domains gives us a lot more insight into what's going on in the channel. So overall, given the proper measurement and the proper tools, you'll be able to extract much information, including material properties, models, and ultimately optimize your channel for the highest speed data transmission that you can get. So with this, I'd like to thank you for your time, and I wanted to make sure that you saw some of the resources that we have available if you found this an interesting presentation. You can make as deep of a technical dive as you would like. We have some very great app notes. We have YouTube pages. We have product pages. You can actually download a PDF of my signal integrity book if you would like. I think they ask for your contact information, but you can opt out on things so we don't send you spam. But there's a lot of good information here, including Tim Wang Lee has a Blackboard with some very good blog information. So I'd encourage you to do more homework and look deeper into this real interesting field that will be here for a very long time. Okay, one of the demos that I was going to do, but I think a live demo is perhaps a bit beyond the webcast tool here. I'm going to talk to the slide if you don't mind. When I talked about physical layer test system software a few times, and this basically can control a vector network analyzer over LAN and allow calibration and measurement and post-measurement analysis. And that one slide that had the picture of all the taped down test cables, well, that was our USB 3.0 testing that we did in our lab in Santa Rosa, probably about, 6 months ago or so. And we got some really interesting data. And what I'm showing here is a single measurement using the PLTS software with a 12-port VNA, and it was that Pixie VNA, the PXI VNA, that was not fully populated up to 32 ports. It was just up to 12 ports because that's all that I needed at the time. And so I was able to test these 3 differential channels inside this USB 3.0 device. And why did I choose 12? Well, the 3.0 spec has a crosstalk spec between the super speed channel and the legacy USB 2.0 channel. And you cannot exceed some level of crosstalk between those 2 channels inside the same device. And so I measured a 12-port VNA with this USB 3.0 device, and rather than going into each separate domain, like time domain or frequency domain or eye diagram, I went to what's called a test template. And this test template was set up specifically for USB 3.0, and it has limit lines that will show a pass or fail for each of these parameters. And what we were able to do is drop that S parameter data directly into the template, and it populated these 8 graphs. And we've got impedance profile in the upper left plot, and then near-end crosstalk in the time domain. And then we had the differential insertion loss. And then in the second row, we looked at near-end crosstalk in the frequency domain, and then far-end crosstalk in the frequency domain. And then this sixth plot was the crosstalk between the super speed and the legacy channel. And then we looked at common mode, and then eye diagram. So these are some of the tools that you can use, and you can imagine, especially if you're testing 100 of these in a production environment, you can get pass-fail criteria with one machine, one instrument, one software tool in all these different domains. And so this can be a very powerful thing. And as we're finding out, a lot of companies around the world that do high-speed digital cable manufacturing are using these exact techniques today to make their job easier and more efficient. So with that, I think that I would like to open it up for any questions that we might have. And again, thanks again for your time.
Excellent, Mike. Thanks for all of that information. All right. Now we ready for questions and answers? When would you choose one VNA form factor over another form factor? For example, PCI or PXIe versus benchtop versus field unit.
Okay, so as I mentioned in one of the slides, we've got a whole family of vector network analyzers. The portable instrument, of course, if you're in the field doing installation and maintenance, we've got these smaller, handheld, ruggedized vector analyzers that actually go up to pretty high frequencies, 50 gigahertz, if I recall. And so that's a great application for a handheld. If you're in a production environment, you're doing high volume, I would suggest the PXI VNA, just because it's scalable up to 32 ports, and you can actually set it up to do like one 32-port VNA, or it can be two 16-port VNAs, or any combination thereof. So it's very flexible for manufacturing. And then the typical benchtop vector network analyzers that you see in the lab are very common in SI labs around the world. So, really any kind of VNA that you need, there's a form factor that fits that application.
Thank you. Next question here. Is there a way to reduce random errors by adding shielding to my test setup?
Yes, there are ways to build Faraday cages that can shield external noise sources. If you're in a particularly noisy environment in your lab, which if you are, you have my sympathies, because that's not the best environment, but it happens. Anything you can do to shield stray radiation and send it to ground is a helpful thing. Now, normally in differential channel design, like we have on backplanes, you have a virtual ground because of the balanced symmetry between each line in the differential pair. And so you should get a natural common mode rejection ratio, or CMRR, off of that well-designed differential pair. However, if that differential pair you're testing in your device is not perfectly symmetrical, you can have what's called mode conversion, which means that you're susceptible to EMI coming in, and that EMI incident on that differential channel that's not being shielded, then that could convert into differential signal into your channel right along with your data as a small delta voltage and creating error in your receiver. So this is a good question. It's very important as we go into higher speeds to design your differential pairs very carefully so they are symmetric.
Thank you. Do you have network analyzers that go above 120 gigahertz?
Good question. So there are basically two types of network analyzers. There's broadband that go from very low frequencies, take 10 megahertz, all the way up to 120 gigahertz, like that one I showed you with the external modules. Those are called broadband VNAs. That's what we need for signal integrity analysis, because we have to do an IFFT, inverse fast Fourier transform, on that frequency domain data to get our time domain impedance profile. So we have to use these, what we refer to as broadband VNAs. However, for some military applications where you're only interested in the frequency domain, or you just want high frequency banded data, we can go up to 1.5 terahertz. But understand, 1.5 terahertz, that type of VNA is not broadband. That will not go down to 10 megahertz. So time domain transforms on that frequency domain data that's banded will not be accurate. So, but for these military applications, these microwave engineers have been using banded VNA analysis for decades, and they're very knowledgeable about how to use these sophisticated instruments. And but just to be aware, for signal integrity applications, we want what we call broadband VNA instruments.
Excellent. Can PLTS create custom test parameter profiles?
Custom, can you repeat that last part? Custom
test parameter profiles.
custom test parameter profiles. Okay, so that was what I was trying to describe with the USB 3.0 template that was like the last demo slide. So the user themselves can create these. It's quite easy to do, and basically you get what you call your golden prototype. You researched, you tested, you troubleshot. You've got your one device now that works in every one of your systems, and you'd love to build 1 million of these golden prototypes. So then what you do is you measure that golden prototype with physical layer test system and a vector network analyzer. You get those S parameters, and then you start building insertion loss, return loss, eye diagrams, and you put limit lines, you put eye masks, and you define the margin that you want. And many times, engineers will design 3 different levels of quality or performance for one family of prototype, and then you can naturally sort these in different categories. So if you're building the Zowie backplane at 3 and an 8, you may run into some that run at double that data rate, and you want to save those for higher data rate applications. So creating these custom templates allows you to do that sort of analysis, and it really is just very powerful, fast, and simple to create these templates. And we give some away initially when you buy the product. It's in the upper left-hand hierarchical tree, and they're embedded there. Some people don't even know they're there, but we try and teach people that's where they are. But in any case, it's very possible, and it's a very good thing to do if you can.
Excellent. Thank you. Next question. Your paper or your presentation here talked about VNA measurements. What about TDR measurements?
Okay, TDR, time domain reflectometry, typically is done with an oscilloscope that has a TDR plugin module. So there was a picture of our digital communications analyzer, which we call the 86100 DCA, and they've got very high quality TDR modules with extremely fast step generators in them. I think they're down to like 9 picoseconds now, which gives you very good time domain resolution. So those instruments, TDR oscilloscopes, can also be controlled with PLTS software. And you can do the same sort of analysis that you can with the VNA. The advantage is that your DCA will also accept optical plug-in modules. So you can kind of get multi-use out of your mainframe instrument. Do TDR, get the impedance profile, and then with PLTS software, you can do FFT, fast Fourier transform, and get frequency domain data. So there's a one-to-one mapping between the time domain and the frequency domain. What a digital guy calls TDR, a microwave guy will call return loss. What a digital guy calls TDT, time domain transmission, a microwave guy will call insertion loss. A digital guy says crosstalk, microwave guy says isolation. These are all the same parameters, and they just vary with an FFT. And so this can be done mathematically, and they're virtually the same information.
All right. We have about 5 minutes left, so I have just a few more questions that keep coming in. So can S-parameter de-embedding be used for multi-port differential pairs so that crosstalk is comprehended?
So I'm going to have you repeat that one more time to make sure.
Yeah, I'm wondering if comprehended is closed down. So can S-parameter de-embedding, like AFR, be used for multi-port differential pairs so that crosstalk, XT, is comprehended?
Yeah, so the way that de-embedding with S-parameter works is that we're able to remove the structure and look at the resulting channel without that structure in it. And if you have crosstalk that is created by that channel, then that crosstalk can be removed. If you have other sources of crosstalk within the channel, say you have physical asymmetries from a via in your device under test, that's going to still be susceptible to mode conversion and crosstalk. So that's actually going to be still in your channel when you're looking at the result of your device.
Okay. So next question, and I currently perform multi-port calibrations on my system. How often do I have to recalibrate?
The old question pops up again. Well, you know, it's a personal preference, really, and it depends on what you're doing with the data. If you're just troubleshooting and you're learning yourself where the problems are or failures are, you know, you may not need to calibrate. You're looking for qualitative data. You're looking for big reflections or huge suckouts in the frequency domain. Those are things that you can do without calibrating and still get valuable information. However, if you're making big decisions or publishing data, I'd recommend calibrating right before the measurement. You know, frankly, any measurement that I make, I calibrate right before it. And I normally end up spending, you know, one day in the lab, and I'll calibrate in the morning. And I'm confident that if no one has touched my setup and my cables are taped down, no one's bumped anything, I can come back in the afternoon and I can make good measurements from that calibration in the morning. But if I don't know if someone has borrowed some cables or if they moved the device under test and created some phase error by bending a cable somehow, I'd recalibrate. And as I mentioned, with the eCal, the calibration is very fast, even for these multi-port systems. So, you know, why spend all the time and effort to make a measurement if you're not going to be able to use that golden nugget and call it accurate for a long time?
Excellent. Thank you, Mike. We're at the top of the hour, so that is the conclusion of today's webcast. So thank you for attending today's webcast brought to you by Keysight Technologies. Enjoy your day and join us at another webcast. Goodbye.